The AAAS Newcomb Cleveland Prize, our oldest award, recognizes an outstanding original research paper published in Science each year. The winning paper is chosen based on the quality of its scholarship, innovation, presentation, likelihood of influencing its field, and its wider interdisciplinary significance. This year, we present the prize to the paper entitled Seismic Detection of the Martian Core, first published July 23, 2021. The interior of our Earth and other planets has puzzled humans for millennia and has been the subject of countless scientific theories, and before that, of religious and mythical tales. Only in the early 20th century did seismic waves from distant earthquakes confirm that the Earth is composed of a rocky, solid mantle above a liquid core made predominantly of iron. Little did those scientists imagine a comparable experiment would one day take place on Mars. The paper was a core product of NASA's InSight mission, which established the first long-term geophysical observatory on another planet. The goal of this mission was to use seismology to repeat what was done on Earth 100 years before and determine how large Mars' core is, whether it is liquid or not, and from both of these observations, infer its composition. The InSight lander launched in May 2018 and landed on the Red Planet 6 months later. The paper's authors comprise an interdisciplinary group of seismologists, geophysicists, geochemists, and others, led by Simon Stahler, a seismologist and senior researcher at ETH Zurich. With a single seismometer delivered by this lander operating over 50 million miles away, the team was able to learn an incredible amount. Stahler and his colleagues interpreted small ground motions that happen about 8 minutes after a quake. These vibrations are due to a seismic wave traveling to the core mantle boundary and back to the surface. Together with other waves that traveled the direct path or were reflected at the surface, they were able to constrain the interior structure. Stahler and the team narrowed down the core size significantly and found it to be on the larger end of previous estimates, at about 1,800 to 1,870 kilometers. They also confirmed the core is in a liquid state by inspecting the strength of the reflected waves. Finally, Stahler and the team learned more about the core's chemical composition by comparing the density of the planet as a whole with the density of rocks in high-pressure laboratory experiments. Now that they have identified the seismic waves reflected at the core, future researchers know where to look for more subtle signals hinting at the substructure of the core. The InSight team's conclusions have implications for not only understanding Mars, but also for terrestrial planets in general, including Earth and the thousands of exoplanets orbiting other stars. This paper and other work by the team will serve as a roadmap for future planetary missions in our solar system and beyond. Seismic Detection of the Martian Core, recipient of this year's AAAS Newcomb Cleveland Prize.